Well, good morning, everybody. Yesterday, I was like this, okay, as I was mentioning, the whole objective of the two lectures that I am giving would be to give a reasonably, it's a very, very brief this introduction to this classification program and some of this, okay, to give some main ideas about this classification. This is more like just a snapshot from a satellite rather than any kind of a survey. It's a very, very, yesterday I just emphasized that in a group of, in a simple group, the involutions play a very important role. In fact, to start with, involutions exist and most groups, most simple groups, particularly this, most simple groups can be just, most sporadic simple groups can be characterized in terms of this centralizers of involutions. This was like this one big program started by Richard Brouwer, which was extremely successful. And I'll only just indicate another main theme that was started by Fisher, which is in analogy with the symmetry groups. Symmetry groups, as all of you know, is generated by the set of transpositions, which is a conjugacy class of involutions, such that the product of any two of them are 1, 2, or 3. Okay. And you see that this property is the same thing from the diagrams. It's very clear that this is also true for the other Coxeter groups of type AN, DN, and EN. That is the Coxeter groups with a single bond. And the Fisher's initial idea was to classify in the simple groups or classify groups which is generated by a single conjugacy class of involutions with some restrictions on the orders of the products of its elements. He started with something called T-transposition groups. And his classification of T-transposition groups led to 3 new simple groups. And this is so-called Fisher 22, 23, and 24 prime. Fisher 24 is not simple, it has a group of index 2, which is a simple group. And Fisher classified these groups generated by involutions, that is so-called 3 transposition groups. That is a product of orders of any two of elements, either 1, 2, or 3. And if you include 4 also, another new simple group, which is also a very big one, the so-called baby monster, also emerge. And if you include 6 also, baby monster as well as the monster group appear as the groups in the list. And these investigations started by Fisher. In fact, a great part of it was done by Fisher, and then later continued by Aschbacher and Kingsfield led to many geometric methods, which also already is indicated in the fact that the Coxeter groups of types AN, DN, and EN are generated by T-transposition groups. And I would like to the whole point of my thing, and I can hardly summarize the kind of main ideas of this part of group theory, but I will just list a few theorems which I find quite attractive, which follows from the simple assumption that the group is generated by involutions with some restrictions. The earliest theorem of Fisher was just this. You could see that if D is, well, all the groups I'm considering is generated by a conjugacy class of involutions. If T is a class of P transpositions, say that no 3 of D generate the 2 group. See, you see that the conditions only is on the orders of the products of elements. Then you can only have S4, S5, and P is equal to 3. And the second theorem I would like to say is that suppose there is an odd prime P such that the order of XY is a power of P for each X and Y. D is a conjugacy class, yes. All the groups I'm talking about is group generated by a conjugacy class of D involutions, and there perhaps will be some additional like this conditions here. Product 1, 2, or P. P a prime, yeah. Okay. Well, I mean, just in the earlier condition, I don't. Yeah. See, if suppose there is an odd prime P, say that product of x, y is a power of P for each pair of elements, then G prime is nilpotent. See, this condition is very purely in terms of this. Say another theorem. All these things are fairly non-trivial theorems, but I'm just listing them to give you an impression about how powerful like this conditions on this set of involutions would be. Suppose that the distinct elements of D don't commute, and the centralizer of G of X factorizes as its just. Well, this is the largest normal subgroup, normal 2 subgroup in CG of X. This is the largest subgroup of CG of X of odd order. If CGX decomposes like this, then G should be solvable. We see the next theorem. This already just sees this already just like this gives some clue about this like this geometry that would like this enter in. Please remember that the Frobenius conjecture or Frobenius theorem. This was about like this group, a group acting transitively on a set X such that no non-trivial element fixes more than one symbol. That was this like this Frobenius conjecture, which was well, there was the class of Frobenius groups, and the nilpotency of the Frobenius conjecture was a major step in group theory. The next kind of thing that was taken up by, I think, people like Ito, Suzuki, Walter Pite, these people are involved. They were trying to see doubly transitive groups such that no non-trivial element fixes 3 symbols. Doubly transitive groups where no non-trivial element fixes 3 symbols. And this, after a lot of very enthusiastic work over about 15-20 years, just led to this Suzuki's discovery of what are known, not very surprisingly, called as Suzuki groups. That is that infinite family. Of course, the fact that it has a very geometric kind of interpretation and so on is a different story. It was discovered later, but it was Suzuki groups were discovered as this doubly transitive groups so that no non-trivial element fixes 3 symbols. And another class of permutation groups on which which had which gives rise to a lot of geometry and lot of simple groups is 3 transposition groups. That is a transitive group such that the stabilizer of a point has only 3 orbits. Okay. And this, for example, you see this theorem, let E be a set of pairwise commuting involutions of D of maximum size n. Okay. So G is a group generated by a conjugacy class of involutions. You are looking at the set of pairwise commuting elements of maximum size. Then normalizer in G of E contains a silo 2 subgroup of G. Normalizer of G, E acts 2 transitively on this. And normalizer in G over CGE is isomorphic to one of these list of groups. And okay, this is okay, for x belong to D, dx is this, fx is this, then dx acts transitively on dx as well as fx. That is actually transitive. Well, this group G is and G acts on D by conjugation as a rank 3 permutation group, and okay, this its 3 orbits are as described here, and this is the main theorem of rank 3. It's a permutation. It's a transitive permutation group in which the stabilizer of a point has 3 orbits. Okay, and this is this main theorem of first main theorem of Fisher. Suppose G is a group generated by a conjugacy class T of 3 transpositions, then he just gets this list. But you see that many of the groups that you have here, these are just classical groups. Just Sn, of course, symplectic, unitary, and orthogonal groups. And it also just leads to 3 just new main groups, that is new simple groups, which is just discovered only by this analysis. And of course, just well, I mean, there are later, just the ideas introduced by Oshbacher and just Kingsfield. This generates new geometric ideas, which essentially classifies, which led to identification theorems for this classical groups. And this also led to looking at the right centralizers to get this baby monster and the monster. So I think I'll just leave it at this, and I think just okay. I think I should just make some remarks. Well, the whole idea of just giving this lectures on this classification was to introduce the most attractive of the objects, the monster. Okay. And there are 2 great aspects about this monster. Of course, monsters construct quite monstrous, but it has lots of connections with other areas of mathematics. Number 1 is that there is something called monstrous moonshine. Okay, that is connecting the monster group with modular forms, and this is the conjectures by Conway and Norton, which was proved by Borchert, for which he got his Fields Medal in I think 92 or something. That is one aspect which leads to the theory of Virasoro algebras and just the string theory and so on. Unfortunately, we have been able to just find what's his name? Gopkumar. Yes, Professor Suresh Govindarajan to give 2 lectures exclusively on this monster and its connection to string theory. The another aspect here is that the monster acts on a very large algebra, this so-called Griess algebra. And I'll try to go as quickly as possible to give some indication to these things, and which of course can be only scratching the very surface. Well, this group, this monster group is an extraordinarily attractive object. Just this, and it was predicted by Fisher and Griess in 73, and its construction was done by Griess in 1980, and it acts as the automorphism group of a non-associative algebra of this dimension, which of course is called Griess algebra. Well, I mean, just the order of this group, I'll tell you a few very interesting aspects of this, which is rather very well known. You just see that the order of this group is not particularly very small. Okay, it's very huge, 10 to the power of 53, which people just, okay. It's a huge group. It can hardly be handled by, it is a finite uncountable group, I think, which is a fairly accurate description. The outer automorphism of this is 1. Its Schur multiplier is trivial. Okay? So it doesn't have any non-split central extension. The degrees of 2 smallest complex irreducible representations are itself is pretty large. So if you try to realize this as a matrix group, you should be thinking of very huge matrices. It has a unique complex irreducible representation of this degree. In fact, that degree is the smallest of the degrees of its non-trivial irreducible representations. And assuming its existence, its character table was calculated by Fisher, Livingston, and Thorne. And well, I mean, just Fisher's and Griess assumption to start with was only a centralizer of an involution. With that, they deduced that there should be the character of that size, and much more of the structure theory of that was obtained by assuming that there exists a group which admits an irreducible character of that degree. And Thompson's uniqueness proof of this group, as the group satisfying some conditions posed by the internal structure, which was reduced by assuming that the group had a certain centralizer of an involution, and its subsequent construction due to Griess started with the assumption that it has an irreducible representation of this group. One, of course, everything about monster is very remarkable. Its construction, I mean, I'm only talking about one construction. There are just three constructions of this. One using this Virasor algebra and one other the so-called monsterly algebras, about which I don't talk anything at all. But the construction of Griess itself involves very, very remarkable mathematical structures. This is this binary code about which I talked very briefly yesterday. This extra special two groups, the Leech lattice, and the so-called Parker law. Okay. Its permutation representation of smallest degree can be realized on a conjugacy class. It's okay. The monster has two conjugacy classes of involutions. Okay. And one of them is this so-called like this. One is called Conway conjugation, Conway involutions, and another is Fisher involutions. And the action of this group on this conjugacy class of involutions, this actually led to Norton like this, showing that there exists a permutation representation, there exists a complex representation of that dimension 196,883. Okay, this has some very, very remarkable properties. This is, I think, as far as simple groups, E8 over any field, and this monster are perhaps the groups which exist, manifest the leap phenomena and the sporadic phenomena to the fullest. And it has 194 conjugacy classes. For a group of that size, this is a very, very small number. Please try to imagine how many conjugacy classes you have in an abelian group, or a T group, or a solvable group, and this is a very, very small number of conjugacy classes. And it also has maximum subgroups of very large indices. Very, very small groups appear as maximal subgroups, which doesn't happen, in more solvable or more like this. And its structure is very, very intricate. Not because it's large, even alternating groups of size at most 50 has a comparable order. The 20 of the 26 sporadic simple groups, they just lie as sections of this group. Section, what is a section? It is a factor group of a subgroup. The factor group of a subgroup. That's a section of it. Okay, some subgroups, following simple groups are involved in M okay. I mentioned this like this Conway involution. Its centralizers is like just, it's a normal 2 subgroup, and this happens to be an extra special group of order 2 to the power of 25, extended by this Conway group. Okay, and as you see, quite a few active groups appear, quite a few simple groups appear as well, quite a few active sporadic simple groups appear as sections of this. And I will say a little more about this. Following simple groups appear as centralizer of an element of order, the centralizer of an element modulo the subgroup generated by this for these orders, and all these groups are actually simple. Well, of course, you could one can you know the order of the monster, you could look at the simple groups whose orders divide mod m, and well, this is not a complete list, but I think you can see that a very large number of classes, ANs and the matrix groups also appears as subgroups of that, which makes its structure rather quite naughty. And also, I think, just as anybody who has just dealt with this non-split extensions, it's very difficult to just prove that in situations non-split extensions exist. And quite a few non-split extensions like this appear as sections of this monster. And in this way, constructing the monster like this proves the existence of not only the 20 sporadic groups that are involved in that, but also these non-split extensions. Sorry? Well, I told you, it appears as a section. But of course, this is one thing which has created a lot of jokes about this monster and so on. And well, I mean, just the prime divisors of the monster, the prime numbers which divide the monster, and the set of prime numbers such that certain modular form has 0, 0. Okay? This set of numbers just like this are exactly the same. This set of prime divisors of the monster is the same thing as the set of all primes for which just certain Riemann surface associated with a modular group is like this 0, 0. And this was like just the Ogg's observation, but by that time Thompson and other people had already calculated the order of the group. So this is an observation of. Well, another thing is that it's very difficult to prove when a group appears as the Galois group of an extension field of Q. And there's a fairly simple argument to show that the monster appears as the Galois group of an extension field of Q. Okay. And this is just one of this main success of Thompson's method he developed to just create just when a group appears as the Galois group of an extension field of Q. Well, this is this is another very simple thing. This is a very important thing. A P group in which every characteristic abelian subgroup is cyclic. A P group in which every characteristic abelian subgroup is cyclic is called a group of symplectic type. Many of them appear in sporadic simple groups in a very big way. Any such group is either a central product of an extra special group and a group which is either cyclic or it's a two group of maximal class. This classification is due to Philip Hall. And for any group, you just define sigma of G to be the set of all primes, such that there is an element X of prime order, that order P, such that the generalized fitting subgroup of centralized in G of X is of symplectic type. That is described here. Okay, so it's a set of primes associated with a group in terms of this structure of the centralizer of an element of prime order. And for example, for the monster, it is this set of primes. This seems to be the largest set of, and there is a conjecture of Thompson which says that if the number of elements in this is greater than or equal to G, then G should be necessarily the monster. And in the case of this monster, see, corresponding to these involutions, you see that the centralizer in G of X's have these structures. I mean, this is the centralizer of a Conway involution, and these corresponds to other primes that exist. Well, there are some very, very remarkable coincidences, which very few of which has a proper explanation. The first one is simple to state. Let's say that A1 is a set of all primes, so that P minus 1 divides 24. Okay? So that is exactly this set of primes. You remember that this is the set of primes that appeared in my earlier list also, when I just. And A2 is the set of all primes such that this modular group is X of genus 0. And well, these conditions are a little technical. A4 is a set of M contains an element of order P such that its centralizer is isomorphic to this. where 2d into p minus 1 is 24, that is, it just gives the size of this extra special group, and yeah, and GP is in this list. Well, all these are supposed to be sets are supposed to be the same. As I said, M has two conjugacy classes of involutions. One is this Fisher involutions I mentioned a little earlier, and the Conway involutions. The fact is, if you assume that G is a simple group which contains a involution with this centralizer, then the monster is uniquely present. You see, okay. See, it has also elements of order 3 whose centralizer is an extension of the Suzuki group by an extra special group. And you have similar things for the other primes which divide, that p minus 1 divides 24, that is 5 and 7, I think. And they also just lead to simple groups, that is the so-called Thompson group and the Harada group, which is involved in the monster. And somehow this special property of this number 24 seems to have some very important significance. 24 is characterized by the property that the divisors h of n are precisely those integers for which this congruence implies this congruence. Okay. As I said, well, I'll come to this later. You see, okay, this M is a 6 transposition group. What does that mean? It is a group generated by a set of involutions, so that the product of any two involutions is at most 6. Okay, at most 6. So this the Fisher involutions. You look at this conjugacy class of Fisher involutions. If you look at the products of elements, just it falls into 9 conjugacy classes. 0, okay. And the products of elements, products of pairs of elements are like this. As you see, none of them is more than 6. So M is a 6 transposition group. Further, these numbers are exactly the degrees of irreducible representations of the binary icosahedral group. Okay, this is another strange thing which we are thinking. And the products of distinct elements of F are in different conjugacy classes. Well, this notation is from Atlas notation. And the structures of these respective centralizers of M are these things. Well, the main point here is this. Norton determined the number of triples x, y, z in F, so that x, y, y, z and zx are in specific conjugacy classes. Okay. And this gives the intersection numbers of the centralizer algebra of the permutation action of M on F. And from that he could deduce in a reasonable way that this algebra must have, this centralizer algebra corresponding to the action of M as a primitive idempotent of this dimension. And so M has this irreducible representation. Well, okay. This is another very important connection which has not been observed. Yes, character table is known. Okay, this is this correction with this E8 latest. Well, it is the affine Lie algebra. Okay, let's say that these are the fundamental roots in the root system of this, and alpha m is the maximal root in this, and you have this relation. And the point is that conjugacy classes of elements of F cross F, they can be accessed indexed by, okay, these access vertices of this affine E8 diagram, they can be accessed indexed by the conjugacy classes of elements of F cross F, okay, which is the same thing as it can be accessed indexed by the conjugacy classes of products of involutions in the conjugacy class. Well, this is just something about so-called the associated modular forms and so on, which I'll just give. Well, Glauberman and Norton have many more observations about that. Well, I think Moonshine, so-called Moonshine, I mean just typically Conway, just monster, baby monster, Moonshine, we are all just doing all this very characteristic of Conway, I suppose. And I'll just very quickly go through that, because I think we will have just a couple of lectures on this Moonshine. Okay. Well, see, this started with this great observation that 19,664 is 1 plus 19,663. Okay, that was discovered by Mckay, and he just wrote about that to John Thompson. And but the point is, the coefficient of Q in the elliptic modular function JQ is 1 plus minimum of the dimensions of non-trivial complex representations of F. Okay, that's the point. And Thompson, just thought that there is something very significant, and he pointed out that the next few coefficients of that modular form are also simple positive integral linear combinations of the degrees of some irreducible representations of F. He suggested that there might be an infinite dimensional graded algebra such that the dimension of this Wn is the coefficient of 2 to the power of n minus 1 in J of Q for each n. Okay. And this is actually the basis for looking for a infinite dimensional graded Lie algebra, which was constructed by Lepowski, Borman, and so on. And Conway and Norton calculate the first few terms of the Mckay-Thompson series above by making reasonable guess for the decomposition of the first Wn's into direct sums of, okay, these things are actually the coefficients of JQ, and all the numbers occur here are actually dimensions of irreducible representations of the monster. And by calculating, they found that the Mckay, this is what they call the Mckay-Thompson series. So for any element of the group G, we look at this function where the coefficient is the trace of G on Wn. Okay, Wn is actually the nth module in the circus, that graded thing, and they seem to be half modules of genus 0. On this basis, the famous Moonshine conjectures were made, and that was proved by Moonshine. Well, this is the explicit conjecture, which is a theorem now, and I think I'll not go over more of this because I think there will be more detailed lectures on this. Okay, I think I'll come to the discovery of M later. Well, as far as this the construction of the monster goes, this is as I said, this is the amalgam of these three groups. Well, constructing each one of them itself would take quite a good deal of work. But they are extremely naturally occurring kind of things. They are the amalgam of three groups with these properties. So let's very quickly go through what an amalgam is. Suppose you have accessed groups. Assume that the set of elements of GI have pairwise non-trivial intersections, such that at the intersections, the products of X and Y coincide. Okay. The completion of the system is like just a group with a map from G1 union G2 union G3 to G, which has this property. That is just the psi of X into psi of X, this psi of Y in the group G is psi of X. So X and Y are just elements in GI. You look at their product, you look at their image, that agrees with this the product of the image of X and Y in G is called the computational. And just the natural definitions of faithfulness, generating universality, and so on. And the object here is to just construct an amalgam of those three groups, which came from the local structure that was derived by assuming that the existence of the centralizer of the involution. And just the algebra that was constructed by Griess. This was I told you at the very beginning that it is a commutative associative algebra. And I'll just try to give some indication about why that was looked at. So let's go through some generalities. A is an algebra over K, this is a bilinear form, and B is a linear subspace of this. And if you have the projection P from A to B, an orthogonal projection, and then if B is not okay. If B is a non-singular thing, this decomposed is unique. If G is a group of automorphisms of A, preserving this, we can define a G algebra structure on B by defining this. You take the product of X and Y in A, and X into Y is the product of X and Y and its projection into A. Well, this is called the restricting. Well, this is the idea to start with. So just look for this. Simple examples of this are this Jordan algebra structure of symmetric matrices and V algebra structure of two symmetric matrices. Okay. But the point is, you see, they started with the assumption that there exists a irreducible representation of degree 196,883, and so it acts on a complex space. Its character table was known. Norton showed these properties. Chi of G is always a rational number. It appears with multiplicity 1 n, its symmetric square and symmetric cube. And these are the observations which gave the hint to look for a commutative associative algebra. Let's look at some very, very basic things. Recall that psi is a representation of a group G and a vector space W. Then H from W cross W star to C. This is a chi W invariant non-degenerate bilinear form. And two irreducible complex representations are equivalent if their characters are identical. This is what we know, what we learned from our first course. So the representation theta of M is irreducible and its character is equal to its dual by 1 by the first observation of Norton. Theta is equivalent to its theta star. So V star can be identified with V. So this identification allows us to assume that V admits a theta M invariant symmetric non-degenerate bilinear. Okay, so on this on the assumed irreducible representation vector space of dimension 196,883, you have this much now, theta M invariant. And as I said earlier, a multiplication on K algebra. What is a multiplication on a K algebra? It's a mapping from A cross A to A. The map alpha is distributive if and only it factors through A tensor A. And the multiplication is commutative if it actually factors through S to symmetric square. Thus, any k-linear map from S to A into A defines a commutative multiplication on this. If A is a G module and K is KG module morphism, then that multiplication satisfies this problem. But you see, for our irreducible representation, we just, Norton had verified that the irreducible representation appears with multiplicity 1 in this symmetric square of that representation. And that is the reason why we. So since this is 1, the projection map from S square V into V, this defines a commutative M invariant multiplication on this V. That is, we have multiplication with this property. And also, the character appears with multiplicity 1 in the symmetric cube. And of course, we just have this. This is the same thing as this. So that just allows us to define a mapping from V cross V to V, so that f of x dot y that is. So I think from the character and certain things that they can calculate about these characters, you could actually see that there should be a commutative associative algebra. Okay. Now I'll try to tell you something about the heuristics, or just how just Norton could see by looking at the action of the group on this Fisher involution, that there should be just a representation of degree 196,883. Well, this is essentially a repeat of what I just said earlier, but let us look at some generalities and permutation modules. So you have a group G acting on a set omega. You look at this free vector space on omega, complex free vector space. So there is an action of G on this, and omega cross omega just decomposes. Sorry, this is supposed to be union R. This decomposes into R, C orbits, say. And this AI is the matrix corresponding to the characteristic functions of these orbits. And A is the centralizer, the commuting algebra of this representation. So it is a set of all endomorphisms of W of this vector space, which just commutes with this G action. And well, this is all just very, very standard stuff. I'm just recalling to give some feel for all these very strange things here. So W and A are semi-simple CG modules, and the degrees of irreducible constants appearing in W are the multiplicities of irreducible representations of A and vice versa. So this is the main point that we actually going to use. That is, the degrees of the irreducible constants appearing in W are the multiplicities of the irreducible representations of A and vice versa. And okay, so in this algebra, you could just consider, calculate something called Hickman invariance, which is just the coefficients that appear in these products. AI, AJ is HIJ, K, AK. And using these things, you could just work out this structure of this algebra. And as I said earlier, the M acts on F by conjugation, and these are conjugacy classes. And this Norton determined these numbers. X, Y, Z, the number of triples that X, Y, Z, and Zx are in specific conjugacy classes. And by this, he could just deduce the intersection numbers of the centralizer algebra, and thus determine the structure of this permutation. And he just showed that there is a primitive idempotent of this degree. So I think it has M has a irreducible representation of that. But there is another proof. Of course, Norton's things. There is another proof in the work of Griess, Meyer, Frankenfeld, and Segev, where they actually show, well, they just prove the existence, prove the uniqueness of the monster, and that in particular exists. Well, I don't know, this is actually one other little mystery. See, well, the Griess algebra construction made use of this sum. He just like this takes the vector space V as a sum of three subspaces of actually these by looking at the structure of the Gole code and some aspects of this language, that is, he constructs actually subspaces of these dimensions, and then he just creates the larger. But this number also has a decomposition like this: 49 into 59 into 57, and these are like just whether there is like just anything interesting about the Griess algebra in terms of this. I think this Ivanov, who of course is one of the major workers in this subject, he's going to, I understand, he's going to just talk about some aspects of this Griess algebra, this so-called like this Roma involution, how to understand the structure of these things. And so I think just we'll get to learn more about the Moonshine as well as the Griess algebra. And I think I'll stop.